with the ESDA, the Education for Sustainable Development in Africa program at the Wangari Maathai Institute of at the Wangari Maathai Institute. So again, the notes will be a bit light. I'll try to explain as much as possible, but there'll be some diagrams which we shall use to explain the concepts. So what we're looking at here is network analysis. Networks are made up of nodes and edges which connect the nodes. So there are many other things that can be modeled using this, including spread of diseases. You can, in business and social media, you can also use this to model the systems there and get some insights into what is happening. So there are some concepts here which we shall use as our central concepts. One is centrality. We'll explain that later. There's connectivity, just picking up how connected the people are in that can be measured in different ways. And there's finding communities or clusters. And once all this is done, you'll be able to figure out if it's an information network, you can figure out the flow information within the network. So for instance, finding the shortest path between two nodes and so on. So in our case, we will focus on football. The players will be the nodes, and mostly the edges will be the passes, but they can also be connecting players to other kinds of events like fouls and goals and so on, or shots. So I don't know if I need to draw anything on this, but that is basically what a network is. It's a set of nodes. The nodes are connected by edges. In our case, the nodes are the players. And in most of the graphs, the edges will be connecting. The players will represent passes between the players. So there are two cases you can look at. There's the directed graphs, which can show the passing tendencies. So directed graphs have the edges pointing in a direction. For instance, if I am passing to a teammate, the arrow will point towards the teammate. The pass comes from me towards the teammate. The arrow points towards the teammate. Now, it's possible for the passes to go back and forth between teammates, and that is also counted as a connection between the teammates. And now the thickness of the arrow or the edge indicates how often the passes are between the teammates. So where there's a lot of thick edges, it means those teammates have a lot of passes in between them. They pass to each other frequently. So the other one would be undirected graphs. The undirected graphs do not bother on the direction of the passes. It simply shows whether there's any passing at all between two players. So here's an example. This was picked from the match between Croatia and France in the 2018 World Cup, I think. So and plotted in Python. We shall see this how this is done in Python. Now the positions of the players are not random. They are the average positions of the players across the match. So this kind of tells you like if a player is here, it means they were not too far from this location during the match. They hang around here. So this is the average position across the whole match. And that's the same for all the other players. So you can see maybe the strikers are the ones who are closer to and the goalkeeper. This must be the goalkeeper thing. They seem to have a lot of back passes to the goalkeeper. So another thing you can do is analyze the density of the passes using heat maps. Now here we have plotted the heat map for Croatia on the left here, and the heat map for France on this side. So for Croatia, you can see there's a high concentration of passing here or in this location. and not much elsewhere. So there's only one hotspot. There's still more passing elsewhere, but the concentration seems to be mostly around here. This yellow shows where there's higher concentration. The other colors, as it goes out, the darker it gets, the fewer the passes in that location. For France, there are two hotspots. There's one big one here, and there's another smaller hotspot for passes around here. There seems to be another slight, not so hot, but another center for passes around here for France. And this may be useful to coaches if they want to analyze the match later and see what changes they can make to their games. So visualization will help them highlight areas for improvement and also identify their key players. So we've talked about directed graphs. They show the ball movement, which direction the ball is going when they're passing. It can also indicate whether they tend to pass backwards, they move the ball backwards or forwards to attack, and so on. Weighted graphs show the frequency of passes. Now you can use either numbers to indicate how many passes are there between players, or you can use the thickness of the edge connecting the two players to indicate whether they had more or fewer passes between them. So it depends on what kind of visualization you wish to use. Now, if you have a very dense weighted graph, it means it's a team that likes this possession style football. And if a network is not very dense, maybe it's a team that prefers to do counter attacks and less of a possession style football. So you have another type of graph, which we call the bipartite graph. Bipartite graph will consist of two sets of nodes. So in our case, we have two sets. You can see the blue nodes indicate the players, and then the green nodes indicate the events. So for instance, this node here indicates shots, and this second green node indicates the fouls won. And any player that won a foul is connected to this node here, and anyone that took a shot at goal is connected to this. So you can see Giroud shot at the goal, but he did not win any foul, I think, in this game. Pogba did both. Pogba won a shot at goal, and he also won a foul or some fouls. This one doesn't quite count the number, but it just indicates that they won fouls. It's possible to draw a graph which indicates how many, and so on. This one simply tells you whether they won a foul, at least one foul or not in the game, or made at least one shot at goal in the game. So then there are certain measures you can compute from the network. One of them is this degree centrality. Degree centrality simply counts the number of connections a player has to the other connections. In our case, the connections here would be the number of passes from one player to the others, as long as the passes from other players to the same player. So those who have more passes to them will have a higher value. So for instance, we have this last one, I think, is highest. I forgot to order them in descending order so that we can pick out the ones with the highest. The highest seems to be 1.5 here. So this Antoine Griezmann seems to be, he has a lot of passes going to him, as well as Hernandez. It's not too high, it's about 1.3. Also, Paul Pogba has a lot of passes going to him. Being a striker, I guess that's reasonable. And there's the one here, Nzonzi, Christopher. He also has it's a little higher than the others. Not as high as the 1.5, it's 1.3, but this must be, I think he's a midfielder. So the midfielder also has a lot of passes going through them. So the degree centrality simply counts how well connected one is to the other players in the team. So the more players you are connected to, the higher your degree centrality. There's one more measure which we call the betweenness centrality. So this one sort of looks for the playmakers. for playmakers who act as bridges between. So, for instance, you can have a group of players on one end and another group of players on one end who form a community. Then there may be one who connects them. So such a player is quite central. So this betweenness centrality is able to identify such a player who is kind of a bridge between two communities. So this can be the midfielders. The midfielders act as a bridge between the defense and the strikers. This betweenness centrality measures that it ranges between 0 and 1. 0 means the centrality is pretty low. It means very few passes go through that player. And 1 means almost all the short paths between any pair of players go through that player. So this is more like what you would call a bottleneck in management. Or if this would be either a bottleneck or someone like a project manager who connects different teams. So everything from this team to that team goes through the project manager. So this betweenness centrality picks up that aspect of the network. I hope that makes sense. This can be done in more detail. The idea behind these talks are for the general audience, so I'm leaving out a lot of details, but I hope the point is getting across. So the higher the value, the more central or the person is. So in this case, the midfielders, these are the people who control the tempo of the match in terms of football. So in this one, the one that has the highest was what? Again, it's Christopher Nzonzi who seems to have the highest. I think Christopher is a midfielder. Those football fans should know this. I don't know which team he plays for now. This was in the World Cup, but so this only picked the France players. I think it has not looked at the Croatia team. Okay, can get rid of this. So the other thing that you can look for in a network is the shortest path between players. As a coach, this may be of interest to make the play more efficient. It's good for really fast ball movement to make your attacks faster and also reduce the reaction time of the opposing team. So in this case, you may not be able to see the names. The font is a bit small. But here what I did is try to track the shortest path between Blaise and Mbappe. So it just goes through Giroud. From Blaise, it goes through Oliver and straight to Mbappe. So the shortest path from Blaise to Mbappe is only two passes. There might be other pairs of players who have longer short paths between them, but this one is just 2 paths. So when you identify these short paths, it can enable very effective counterattacks, which are fast, and the opposing team may not be able to respond in good time. So that's the other application you can do. Again, there's a lot of behind the scenes mathematics that happens here. I've left it out just because we're more interested at the conceptual level. So the other thing you can pick up is small cliques within the network that are very connected. So this one picked up 2 cliques. This first one has how many players? 1, 2, 3, 4, 5, 6, 7. So these 7 players in yellow form a community. So the communities do not have to be very strongly connected in the sense that not all players must pass to each other, but somehow there is a path that moves from each player to any of the players within that community. So this picked up 2 communities. I think I didn't bother to check which ones they are. It could separate, say, defenders and maybe the midfielders and attackers. So this is the one for Croatia. It picked up, I've shown the one for Croatia only. It picked up 2 communities, as you can see. So these communities also help the coach figure out which players play better together, which ones seem to connect more, and so on. So you can also pull out smaller subgraphs and see how well connected they are. Sometimes this helps you to identify players who are isolated during the game. So all this information can be applied to scouting, maybe analyzing the opponent's games so that you can develop strategies to beat them. It can be used in corporate structures to identify bottlenecks. If there's you analyze the management system, using the networks, you can see if there's a bottleneck that needs to be gotten out. So the bottlenecks are identified by the betweenness centrality, which we talked about earlier. The higher the value, the stronger that bottleneck is. The other places it can be applied as well, there is epidemiology. You can study the spread of diseases with this. You can study communities within the social networks, these Twitters and Facebooks and so on, even LinkedIn. You can study all that using network analysis. So I've oversimplified everything. I hope it is not confusing or. But if you have any questions, you can ask. So this just repeats what we have said, that it's quite applicable, this network analysis in soccer, and how you can visualize the network to better understand the game. So this is all I have put together for the talk before we move to the demonstration using Python. If there are some references you can use, you can look at them. These slides will be shared. Henry will, for all those who have registered, will receive a copy of the slides, so we'll be able to download some of these references and read. Then there's this, if you want to learn about network analysis, there is this book by Eric Ma. I think he's the author of, there's a package called NXVs for visualizing networks. He's the author of that package, but he also has published a book showing how to use a package called NetworkX in Python, along with his package, the one he authored, for visualization and analyzing networks. So there's this website which covers, on that website, he has a lot of notes and videos which teach you how to work with network analysis. Are there questions? So I can see there are some questions. Which tool am I using? So there is a package called StatsBomb in Python. The data is also available on GitHub. Maybe I'll share the link to GitHub later. I don't have it now. So this data is available in a package. You can download it in a package called StatsBomb. You will see this when we get to the demonstration in Python. So I'm using Python to analyze the data. So if you want to, the technology involved in recording the movements of the players is maybe quite expensive. So I don't know if you can employ this at the local league. It may be quite costly, but it's possible to use some of there are some models for detecting motion or and detecting objects as well. So they can keep track of an object as it moves, measure distances between objects, and so on. There are packages that can do that, and that's what they use for some of these big tournaments. So, for instance, you can get data for AFCON, you can get data from the World Cup, from the Premier League. I don't have any data from Kenya. I would have preferred to use data from teams in Kenya, but I don't have that. Or rather, I didn't look for it. Maybe I should have focused on that to find it.
Sir, can I just ask a question?
Yes.
For the centrality, are we calculating based of the nodes or the edges?
So there are two types of centrality. The degree centrality counts the edges, the number of passes to a player or from a player. So it just counts the number of edges. The more edges you have, the higher your degree centrality. So the betweenness centrality counts the number of paths that go through a given player. So if you have more, if you try to look for a path between two players and check if it goes, any path between a pair of players goes through this one player. So the more paths you have going through you, the higher your betweenness centrality. So that becomes like a bottleneck in a management system, or the playmaker, for instance, a midfielder in a football match. They connect the defense and the attacking team. So they have a higher degree betweenness centrality. I don't know if that is clear.
Yeah, okay. Thank you, sir. I've understood it.
Yeah. So if there are no further questions on this, we can move to the code. And these slides will be shared, since I think your emails have been captured. So there's a package called mplsoccer. There's StatsBomb as well, but MPL Soccer also has access to the same StatsBomb data, but the other thing it does is it's able to draw the network on a football pitch as well. So you need, this package is required. I'm also doing this on Google Colab. So I will share this notebook later on, and anyone who wishes to try this on their own can do that. Now, unfortunately for this particular application, the code is requires some advanced knowledge of Python. So for those who are not familiar with Python, I think we can just focus on the output and ask questions on the output. It may not be possible to understand the Python, but those who are good at Python, I think you can later on look at the code, Python code. And so I'll just run this to install mplsoccer. So this data is available at this GitHub, GitHub user content.com, StatsBomb, open data. There's a folder here. So there's one file. It's a JSON file that contains the data for this match between Croatia and France. So this will extract the passes between the two teams and draw the network. So here it is. Now it is, I think it has mixed up all the players from both teams, but you can, if you wish, I think at the next point we shall isolate a team. This we have already seen. So the edges, the thickness of the edges here will show the frequency of the number of passes. The thicker the edge, the higher the frequency of the passes between players. This is a bit crowded because it's showing the networks for both teams on the same pitch for the whole match, and giving the position of the node is the average position of the player over the whole match. So it's also possible to pull out the data for the players, which is what I've printed here. So this one shows the list of all the players. So now here we filter by team. We pick France and just draw the network for France only. So I will do that. So this shows the network for France. Again, it shows you the average position of the players during the match. They seem to be more towards the goal. So we can change. If you want to see the one for Croatia separately, we can change this to Croatia and run it. So it's now you can see it's a bit different from, if you had them side by side, I think that would be better, but this is the one for Croatia. You can make it bigger so that you understand you see the networks a bit better, but this gives you a general sense of the concentration of play. It seems to be concentrated around here. So the heat map now brings out that information. This is a heat map for, I think it picks up. I think that's a heat map for Croatia. It has one hotspot here. So you use the kernel density plot from Python to do this. Gives you the heat map. It's drawn on this pitch. So you can change. I think this was the one for Croatia. We can run it because I changed to France up there. Now if I run it, it should this should be for France. Why is it showing team name here? Something is not right. I think this is the problem. Let me remove that. So this gives a passing network for Croatia, and then this gives the heat map for Croatia as well. So this shows you the concentration of the passes. Here the passes are concentrated around here, mostly. There seems to be less activity away from this position. The next one now computes the centrality. So again, I will run this. So this gives you this does the centrality for all the players. I think it doesn't discriminate. But we have listed the top 5. So Ante, Rebic, I don't know how you pronounce these names, has the highest degree centrality. I think it's ordered by betweenness centrality. He has the highest betweenness centrality. So that means he's a playmaker. Probably should be a midfielder or something. So the next one now is a network. It's a directed passing network. This is for France, the France team. But here now we use arrows. Instead of using it's direct, you can see the arrows clearly for the passes showing the direction of the passing. So again, someone can study this and see who's getting more passes. You see, like Pogba has a lot of arrows going towards him, so he gets a lot of passes. There's Lucas here. Hernandez also has a lot of passes going towards him. Umtiti also has quite a number of passes. Now, this passing network can also be studied over time. You can study it in the first 15 minutes, see what was happening in the first 15 minutes. Every other 15 minutes, you keep studying it and see how they shape. We might see some of that later. So this next one again is it's the same passing network, but the thickness of the edges is now used to show the frequency of the passes. Instead of drawing several line passes from, say, Pogba to Mbappe, you draw a thick one. A thick one means it shows you there are many more passes between the two of them. So the other one was this bipartite graphs. So the first thing I've done here is to print the different type of events. There are several events. Some of them I can't say understand. There's dispossessed, there is ball recovery, there is block, there is clearance, there's miscontrol, there's duel, foul committed, foul won, interception, dribble, and so on. So all these events are captured during the game. Now, the bipartite graph will try to connect players to events. In this case, we picked only two events. We picked the foul won and shots. So the reason it's called bipartite is because there are two sets of vertices or nodes. Like these green ones have no connection between them. So they will never be connected. Foul won and shot will not have any edge between them. But then the rest of the players, any edge will be from a player to one of the green nodes. But you cannot have an edge between the green nodes. The same way you also cannot have any edge between the players. So you have two distinct sets, and any edge is from one set to the other set. So that's why it's called bipartite, and it connects players to events. So now you can easily tell who won fouls, who won shots, who shot at goal, and so on. And this is the one for France, I think. Yeah. No, I think this may have covered even the ones for, I think it has combined all of them. We can try to isolate. Let me see. Where is the frame, data frame? So let me see if I add a condition here, if we can isolate just the one for France. We can put a logical condition here. If this works, then okay, so I'll put and. Yeah, so now it has isolated only the France players. So it's easier to see. So you can see like Umtiti won a foul or at least one foul, but never made a shot at goal. But all these others seem to have tried to shoot. Mbappe did both, won fouls. He also shot at goal. And one did both. This Steven Christopher also only won fouls, but did not shoot at goal. I think he plays in the midfield, so he never came close enough to shoot at a goal. So you could do this for Croatia as well. Instead of France, you can put Croatia here. And now you can see the names are for the Croatian team now. So I'll leave it at Croatia. I think when you get the script, you can play around with them. Like I said, the code for this is a bit advanced. So it's so next thing we look at is a degree centrality, but now we use graphs to display. So the graph, from the graphs, the bar graphs, you can quickly see who has the higher degree centrality. So this is for, this even has the highest. Again, this one, let's check. This one captures for all teams. So again, we can add a condition here to isolate for each team. Something is not right there. I need a bracket here. Let's see if that works. I hope I've not made any mistake. So yeah, there's a mistake. Let's check it carefully. No, I can't see the mistake immediately. I'll leave that one so that we don't waste time on it. But now it should pick. It should pick. Oh, my connection is misbehaving. I think there's an extra. Maybe that was a problem. There's an extra bracket there. Yeah, I think maybe now we can try. That seems to have been the problem. So anyway, this covers. I'll leave it with it mixes up all the players from both teams, and you can see this Ivan Rakitic as the highest degree centrality. For France, I think it's Antoine Griezmann who has the highest degree centrality. So he's the one with the most passes coming from him or going towards him. So you could compare the degree centrality separately for each team. That's what is done in this. So this shows the degree centrality, top 5 for Croatia and the top 5 for France. So again, you can map this over time. So this one was mapping the degree centrality every 15 minutes. So this was for every line here represents a player, and then you have different points. This first point measures the degree centrality in the first 15 minutes. The next one, the degree centrality in between the 15th to the 30th minute, 30th to the 45th, and finally 45th to 60th. There seems to be no data for any time after 60, so I could not plot it beyond 60 minutes. The data they have seems to stop at 60. I didn't have time to dig deeper to figure out what was going on. But if you go beyond 60 minutes, it's empty. So you can see some players have varying degrees centrality as you go across. So this green one seems to be even. Rakitic starts off high, then goes down a bit, then gets more passes again, and towards the end of the game, they seem to be all low on degree centrality. Maybe they are tired and they are having fewer passes, or they are defending more than attacking towards the end. So again, this is based on, I didn't have a chance to sit down with someone who understands football better than me. That they would have been better able to explain some of his patterns, but you can pick them up with this code. So next one simply picks the shortest path between two players. In this case, we have picked the shortest path between Blaise and Mbappe. This is what we saw in the presentation. So you can change the names of the players. I think I've listed the names of the players here. So you can pick 2 players from a particular team and use them. There's a part here where you can put in where the pass is supposed to start. In this case, we picked it to start at Blaise and to end with Mbappe. So the shortest possible route from Blaise to Mbappe is what we are trying to track through the network. And then it has been colored red. So this can be done for any pair of players. The next one is, again, betweenness centrality, but this time it's tracked in terms using a bar chart to visualize. So these ones are ranked, so it's easier to keep track of them. I may be moving too fast. I hope that is not too fast. If there's a problem, if you need me to go back, please let me know. I can see there are a lot of comments. Or no, there. Okay, we'll answer this one later. For that notebook is from a previous presentation. Yes, it is available. We'll make it. I think it was sent to all who participated, but we can deal with that later. Let's finish this presentation. Now, you can also detect communities of players who are connected. There are a number of ways you can do this, but there's this Louvain algorithm for detecting communities, which is what we use. Again, this can also happen if you are studying social networks, like if you have data from Twitter and so on. You can be able to detect communities that are closely connected within Twitter, Facebook, and so on. So the same thing is applying football. Here it detects 2 separate communities for France. So I did not bother to check if whether these are midfielders and strikers in yellow, and the rest may be some midfielders and defenders. So it picked up 2 communities that are closely connected. Like I said here, the connection is not as tight as there's another type of community you'd call cliques. Cliques are more strongly connected because they require that every player must have received or passed to one of the other players in that clique. We could try to find those cliques. We try to look for those small cliques for 3 to 4 players, but they were not found. So cliques and communities differ in the fact that cliques are more strongly connected, and everyone is connected to everyone in a clique. In a community, I mean, everyone is connected directly to everyone in a clique, but not necessarily in a community. In a community, there may be no direct connection, but there's a path from everyone to everyone in the community. So maybe we can change this. Instead of looking for cliques of length 3 and 4, we can improve. Let's look for bigger cliques, maybe 6 to 8. So that's a bit high already. Let me say 6 to 7. If we run this, it should be able to find those cliques of players. So this may be useful to a coach. Now it has listed the number. I should change this label from 3 to 4 so that it doesn't mislead. Now we have changed this to 6 to 7. It's taking a bit of time. I hope you can still hear me. Yeah, there it's done. So so here it has listed the number of clicks of different sets of players who are fully connected. And it picks any that is 6 of length 6, consists of 6 or of 7 players. So the first one has how many? 1, 2, 3, 4, 5, 6. So this first one consists of just 6 players. We could check if it's possible to find any of length 5. I can reduce this to 5. 3 and 4 refused. So 1, 2, 3, 4. Yeah, there is 1 of 5. So these are quite closely connected in the sense that it gives you the list of those who are connected. It's possible to also draw the network of these clicks, but I have not. I've just listed the names, not the networks. So they can be drawn as subgraphs. So the next one shows subgraphs. In this case, we are interested in connected components. Connected means there's a path from any one node to for whichever node you start from, you can always reach the other node, any other node in the graph through the edges that are available. So these ones, they are no isolated nodes, no isolated players. So we're not able to squeeze out smaller connected components. Just have one connected component. There's a path from every player from one player to all other players. Every player is sort of connected to all other players through some path. So maybe if I tried a different match, it would have pulled out more than one component if there was some separated, connected, smaller connected components. So next thing we look at is a team shape over time. You look at the passing network over time. There's an error here, but doesn't seem to stop the output. Okay, it doesn't stop the output, but here now you can track the network across time. So here is the past 15 minutes. For the French team, there's quite a bit of activity. It's a little more intense in the next 15 to 30 minutes. And then a little less intense now towards maybe it seems to be more intense among fewer players. A small set seems to be more active than the others. In the 30th to 45th minute, maybe this set of players are doing a lot of attacking. And then 40 to 60 minutes, in the 45th to the 60th minute, this is what it looks like. Again, there's less activity. Maybe they are doing a lot of defending during this time because there's much less activity. You can see there are fewer connections between the players. So the rest was trying to check for time after 60 minutes, and you can see the graphs are empty. There seems to be no data after 60 minutes in the data file. So this does the same, comparing shape over time, but for the two teams. So we have the one for France up here and the one for Croatia down here. So you can compare how the passing network for the different teams progressed over time. So there's one interesting one here between the 30th and the 45th minute. There's the French network seems to be a little light. The Croatian network seems to be a bit dense. So on. Now in the 45th, the 60th minute, both networks seem to be a bit dense. Then you have here you have an isolated point. I don't know if this is the goalkeeper. This could be the goalkeeper, but it's more than one isolated. There's this one, and that one. So if someone understands football, then they're able to they can find this useful to analyze the progression of the formations over the match from the beginning to the end. This one is done in batches of 15 minutes. It's possible to also do it in smaller batches if you wish to do it in 10-minute batches. You can do that, or 30-minute batches, or just do separately for first half and second half. You see the difference. This one, I think, had an error. I was not able to correct it on time. Yes. So I'll leave that one alone. I can't fix it now. I think the rest was just, so this was the one that was tracking, I think, degree centrality over the different time periods. But this one has both degree centrality and the betweenness centrality. The betweenness centrality values are small. So this batch of lines at the bottom for the betweenness centrality, probably it's better if they are separated instead of put together. So the next one separated them. This separates and you only have a degree centrality, so it's easier to follow. Should be possible to now draw a separate graph that only shows the betweenness centrality. So the values are small, so it's not a good idea to put them on the same graph, because then it's harder to look at these values for the betweenness centrality. So I think that's the last thing in my file, but the idea is just to poke people's curiosity so that they can dig deeper and learn more about applications of this to soccer. Again, it's not just soccer where you can apply this. You can apply this to social networks. You can apply this to management. You can apply it to spread of diseases. There are many applications, and there are many other concepts also that can be taught that are left out. I also have not read network analysis for too long, so it's a bit new to me as well. But I thought it would be a good idea to share with everyone else. Are there any new questions? So I'll put the link to this notebook in the chat, and welcome any questions. So I have put the link to the Google Column notebook. There's one here where I wanted to compare home and away matches where there's an error. So I need to fix, I will fix that later. Are there any questions or comments? Was the talk useful or not useful? That is, any feedback would be appreciated, whether negative or positive. So like I said, the code for this is a bit advanced. It requires someone who already knows Python. But for everyone else, I think it's possible to follow from the diagrams and some of the output that we have shared. So, but this is not a comprehensive class on network analysis. It's basically just something to invite people into studying or understand reading more on network analysis and its applications. Someone says we don't have this in the curriculum. No, we teach graph theory in the curriculum. In second year of the Bachelor of Science in Mathematics, do graph theory. Maybe not everyone does it, but it's offered to the Bachelor of Science in Mathematics. They study networks. Or maybe what he meant is they don't study football. So they may not study the football application, but they do study networks and other applications. So Henry, I believe there may be no more questions. I should hand over the meeting back to Henry then, or to close the meeting. Is Henry
Thank you, Dr.
available?
Yes, I'm here. Yes, thank you, Dr. Katenda, for a very interesting session today. So everyone, we are having in the chats, there's a link to register for our upcoming course. And also for those who would like the recordings of the previous sessions, I've also included the link in the chat below. So thank you and have a blessed day, everyone. Bye.